What is prestressing?
Stress is initially applied.
Stress is initially applied. For what purpose?
In order to counteract the tension.
In order to counteract the tension in the case of concrete. But I asked a general question, what is prestressing? I didn't ask you what is prestress concrete. We always move from the general concept to the particular. Can you give some examples of prestressing? You can even go back to history, the earliest example. Or in our day-to-day lives, we pre-stress. Have you ever pre-stressed anything with your hands?
Before exam, a student is pre-stressed.
Oh my God, before the exam, the student braces himself for the exam. You're right, in a way that is. But actually that is not pre-stress because that tension makes things worse. But you're right, we ready ourselves for the shock so that we don't get. I'm not talking about psychological pre-stressing. I'm talking about actual physical pre-stressing. Have you ever done with your hands pre-stressing? Give me an example. From your day-to-day lives, have you ever done pre-stressing? First of all, we have not yet defined pre-stressing, but I assume he said to counteract what? Tension. But we'll modify that. Why do you want to counteract?
Because concrete is big in tension.
You're obsessed with concrete. This concrete is weak in tension, so to counteract that tension, we put it in a condition of pre-compression so that we hope it will never get into tension, right? As far as concrete is concerned, it's that. Now drop concrete. Not another word about concrete. Something else.
Ropes for hanging clothes.
Simplest example. After that, you have to hang them. What do you do to hang your clothes?
Tighten the rope.
You have to tighten the rope because you know it's going to slacken after you hang your clothes, right? So you pre-stress. A simple example. Or even when you wear clothes, your pajamas, you use a cord. So here's a very simple definition of pre-stressing. Pre-stressing is the application of an initial load on a structure or a system to enable it to counteract the stresses arising from subsequent loads during its service period and to compensate for some deficiency in the material. As you rightly said, if it's concrete is weak in tension. So you can put it into pre-compression. It's good. But sometimes we do the reverse. Sometimes materials are weak in compression and we subject it to pre-tension so that after you apply the load, you still have some residual tension left. Right? You don't want to go to compression. Can you give an example of this? Yeah. Cycle spokes. Beautiful example. Can you explain?
Spokes generally remain in tension.
What's the diameter of a cycle spoke? 1.5 to 2 mm, not bad, very good. And if you if you take it to the lab and you know the length of the spoke and you subject it to a load, what will happen to that spoke?
You cannot take complete buckle.
It will buckle. At what load will it buckle? I want you to use your imagination. At what load will you? You are afraid of units and all that. But I want you to give an answer. You guess the diameter, that means you're good in seeing distances, but you're not good in measuring weights. What load will make it buckle? 1.5 mm wire that long.
1 kg.
Let's get into structural mechanics. How do you find out?
Eigen buckling load.
Eigen buckling load. Euler buckling load. So what's the Euler buckling load?
Pi squared EI by.
So your memory is good. Pi squared EI by L squared. So what's the L for a cycle spoke? 1 foot. Now you're going back to FPS system. Anyway, you can guess. You're putting weights and a tuck, it'll buckle. It'll buckle at a very low load. Just guess the load. Anybody?
Around half kg.
Again, you go back to kg. The units of force are newtons. Half kg force, okay? Because in his mind he already put and he knows. You've seen that half kg. Okay, that's a very low load. But in a cycle, how many people can sit without it, and travel? Triples, 3-4 people. That's a heavy load. And the spoke which is touching will probably carry a large. But it doesn't buckle. So how does the system work? It shouldn't work. How does it work?
So it is so designed that all the spokes remain with a state of tension.
How do you do that? Now I'm asking you practically, how is it achieved?
By tensioning all the
How will you do it?
by tightening.
At the center and also at the ring.
And also at least
What will you do? Physically tell me. See, there is no, only you are available, the rim is available, spokes are available, you got to do it.
That's why we are providing tubes, sir. We are doing tube.
And tube.
We will anchor the spoke at the center.
Center.
And then we'll apply.
That's called the hub.
Hub.
And then
Then
the other.
we'll apply the required tension. And then
and the circumference of that.
What's an easy way to do the job without pulling it? Easy way. Easy way. What do you want tension or do you want extension? These are beautiful words. That depends. You by giving extension you can get tension, right? So that's probably an easier way to do it. What will you do? Is it so difficult? Just heat it. Just heat it. L alpha T is your coefficient. Huh? And then it will naturally elongate, then you lock it nicely, and then you don't have to do anything, it will cool by itself. You got the tension. That's how it's done. But you would pull it if you want. If you pull it, it's going to be a mess because, something else, some other disaster may happen. This is easy. It's not, you're not troubling any other. Okay. But if you read textbooks, they go back to history. Have any of you, how many of you read books, novels? I would say only 2 people here read novels, 3. Rest of you read engineering books? Or you don't read anything at all? How has any of you read A Tale of Two Cities by Charles Dickens? Huh? Now he's remembering. Yeah.
No,
Tell us.
I haven't started yet.
Okay. There, the first chapter, I think they read something like it was the best of times, it was the worst of times. It has to do with the French Revolution. So we have a French lady here, you should know. So there's a lady there called Madame Defarge. That's the first thing. You remember? Okay. So in that, the Defarges, the woman is stronger than the men, traditionally, both in France and in India. And so her job is to store wine in casks. I remember reading. So, do you know what the cask looks like? Let's say you have to store liquid in a barrel. The liquid will exert a hydrostatic pressure, right? And it'll open out, it'll bulge out. There are wooden planks which are connected to each other. So you have to you get what is called hoop tension. So you have to give a hoop pre-compression. So maybe there's some pictures, examples. This is the picture. Very nice picture. You've got wooden barrels, you've got metal bands. Just tighten them, then you can, no water will leak, no wine will leak. Simple example, right? By the way, Read that book. How many of you have heard of the French Revolution? You obviously. Do you know it's one of the most powerful movements in world history, unlike any other. And you have to have a taste of history. What's the use of being a structural engineer if you don't know history? So read. What are the three famous principles that emerged from that revolution?
Liberty, fraternity,
Not bad. Liberty, fraternity, equality. In French,
Liberté,
liberté,
fraternité,
fraternité,
égalité.
equality. Right? Remember, these are very important principles, and many constitutions, including the Constitution of India, is based on these. Okay, good. The other example which I just mentioned is pre-tensioning spokes in a bicycle. Now, concrete, so if you read the history of concrete, we tend to give more emphasis to reinforced concrete than prestressed concrete. But historically, both started at the same time. But reinforced concrete took off faster than prestressed concrete. And how old is reinforced concrete, prestressed concrete? What's the first concrete structure ever made?
1850. There was a boat.
How old is cement? I mean, manufactured cement. Which century at least? 18th. And why is it called Portland cement?
There was a village in UK.
Huh?
There is a village called Portland.
There is a village called Portland, and the stone in Portland had the same greyish color as the cement. But you had cement, pozzolanic cement, way back in the Roman period, so manufactured cement came at that time. And then the first known application is actually a kind of a ferrocement boat. And soon after that, people tried making beams. Today we don't remember that history, but the history is very interesting. They realized that there's bond happening, that the steel can take tension. And actually beam theories also came up, so we know Euler-Bernoulli theory came up. It's very interesting history. But prestressed concrete, also they did something like this. Okay, so they actually did what is called pre-tensioning. They pulled the bar. Those days the bars available were only mild steel bars. They pulled it and they concreted the beam. Right? So I guess it's kind of M15 concrete those days. That's all. Yeah. Mild steel and M15 concrete. And it's cast and they put loads on it. You say, I think the earliest loads they put were flower pots and things like that. Then something happened. It worked. Everybody celebrated. But their celebration didn't last too long. Why? So you release a tension, just like you pull it, you release a tension, and then what happens is the bar wants to go back, shrink back to its original length, but it cannot because the concrete is hardened and it's bonded, so it ends up applying compression in concrete. So is there an axial force in the beam? Yes or no?
Yes.
If I say no also, I'm correct. There is no axial force in the beam. The beam doesn't become a column now. Why do I say that?
No external.
Why do I say there's no axial force? There's no net axial force in the beam. Why? Because if I cut a section anywhere, there's no externally applied load, so there's no net force. So what's happening is very interesting. You have tension in the bar, and you have compression in the concrete. At any section, you get a perfect balance between the two. Right? We'll see that a little later. But this didn't work. Although these beams could support load successfully initially, they started deflecting and cracking after some time and eventually collapsed. This is what we call failure, and that failure was very useful to learn, because once you know a problem, once you can diagnose a problem, then you can find a solution. So why do you think this happened?
Losses.
Huh?
Losses.
So the Prestress got lost. But it didn't happen suddenly. It took a little time and it got lost. What happened?
Steel is relaxed.
Steel relaxed. No, that's not the answer. I mean, you are remembering what kind of losses. You know that one of the losses is relaxation of steel, but that's not the reason.
Want to produce some heat can expand the steel.
You have to learn civil engineering, still mechanical. Yeah.
Mild steel will yield
Mild steel will yield.
at a low level.
Obviously, then this pre-stressing operation would have been unsuccessful, because the guy who's pulling it would be going on infinitely back.
Application loaded for the
No. You have to be careful. You should pre-stress it
with some margin.
within the elastic limit. Come on. Otherwise, you lost it. Maybe you can go up to the elastic limit and then only you release it, because you lose something from what is called elastic shortening, because the concrete will get compressed. Remember yesterday we said EA by L, because A is the net area of the concrete. That will happen and you lose a little bit there itself. That's called immediate loss. But there is something that's happening over time.
Molecules of the mild steel are trying to de-stress themselves and they will try to elongate. They try to take out
Simple,
stress.
2 words.
Improper
Creep.
Creep.
Shrinkage.
What is creep?
Strain on the permanent load.
What is creep?
Strain.
Don't give me.
Okay.
I'm a layman. I've heard this word creep. It gives me a shiver when I hear creep. Creepy guy. Don't tell me strain on and all that. What is creep in any material?
Time-dependent accumulation of strain.
Time-dependent accumulation of strain under a constant load. Give example.
Even benches, if you see after some time, it may just
Wonderful. So, you've used wooden bookshelves?
Yes.
So you've seen the planks. Why computer tables? When you buy it, everything looks good. Then you put your computer on top of it, and you see gradually a phenomenon that it starts deflecting, right? So they sell it well, but then they don't reveal this secret. You know, if you use books, you put a lot of heavy books. Why does this happen? Creep. I mean, it creeps. Creep gives you a feeling of movement over time. Movement over time. Why does creep happen? And concrete is famous for creep. Steel doesn't creep. Concrete only creeps. Why? Steel relaxes. That's the counterpart. We'll see that later. Steel and concrete doesn't relax. Concrete creeps. Why does concrete creep? Which means, to take the same analogy, let's say you want to build a very attractive car porch sticking out, big cantilever, RC. Well, be careful, because like that plank which deflected after some time, it'll look ugly, it may not fall down, but you have creep deflection. Huh? Arey yaar. Which property is largely responsible for creep? Solid things should not creep. In concrete, there is. What's the difference between concrete and steel? Concrete is heterogeneous. So there's something in the concrete which presence of water, cement paste, those things bring in a fluid-like behavior in concrete. So the property is viscosity. You understand? The aggregate doesn't creep, but the binding material will creep. I'm not going to atomic level. Let's stay at the macro level. So it's the presence of water and the cement paste, cement hydrated paste, which creeps. But a more simple example to understand creep is you all have eaten chapatis. How does chapati come from? The material.
Stone.
Wheat, atta, dough, right? So let's make dough. So you have to mix that wheat powder with water and roll it up into a dough. Let's say you make a little small cylinder out of it. And you keep some weight on top. So the original height of the cylinder was so much. What do you think will happen over time? It will go down. You can intuitively know this will happen. That's great. But that's pretty obvious in something like the dough, because it's a soft material. With concrete it's difficult to visualize, but though concrete is solid and hard, there is a soft thing which you don't see inside, which has a viscous property. And so you have both these properties. One is more important, one is useful. That's called the elastic property. The other property is the hidden viscous property. So you can model this as a viscoelastic material. Viscoelastic material. Okay, that's all. By the way, but you should have some general understanding of creep. So we answered this question. Creep is one main reason. There's one more reason. I mean, they figured it out after some time. They didn't get the answers immediately. And they said, we have to crack this problem. What's the other reason? Another peculiarity of concrete. Shrinkage. What is shrinkage? Give an example of shrinkage, a day-to-day example of shrinkage. Yeah, when you buy a shirt, cotton shirt. Nowadays, I think it's not that. Earlier, you want to check the right size, but after you've washed it a few times, you'll find it's become very tight. So normally, you're advised by a little 1 centimeter more because the cloth will shrink. Yes or no? So some materials shrink. The water evaporates. So in concrete, there's plenty of hidden water. That water evaporates and concrete shrinks. We'll study shrinkage in detail later. So in both cases, there is a movement inward. So there's a pre-compression in the concrete, and so it goes on shrinking. There's an evaporation of water, and it also shrinks. So when the concrete shrinks, the steel also shrinks because steel is bonded to. So when the steel shrinks, what happens? That extension which you gave it initially gets reduced, and at some point it gets lost. Then there's no more prestress. Gone. Goodbye. Concrete shrinks with time. Moreover, under sustained load, the strain in concrete increases with time. This is known as creep strain. The reduction in length due to creep and shrinkage is also applicable to the embedded steel, resulting in significant loss in the tensile strain. In the early applications, the strength of the mild steel and the strain during prestressing were low or less. The residual strain and hence the residual prestress was only about 10% of the initial value. You understand? 100% and then what you are left with 10. 10 is very little to take any load. This is approximate. So residual strain in steel is equal to the original tensile strain in steel minus the compressive strain due to the short-term loss. I told you EA by L, the elastic shortening, minus the long-term loss of creep and shrinkage. This they figure out very quickly. Now we are engineers. I think let's do some quick rough calculations to show this. So to save time, I'll give you the calculation. The maximum original tensile strain in mild steel is, the allowable stress. Well, they also followed allowable stress. What's the yield strength of mild steel? Around 250 megapascals. In the working stress method, they used to allow you to stretch up to 130, 140 megapascals. You remember that? So let's take 140 and then divide by the elastic modulus, and then you get strain. So you've stretched your steel initially by 0.007. You must be good with these numbers. You could be asked an exam question where you have to figure it out yourself. Now, if this is lost, it's lost. So what happens is, the total loss in strain due to elastic shortening, creep and shrinkage was also close to this, maybe just 10% less. And thus there was no significant residual strain for prestress. Now the next question to ask is, we need to change this. Imagine you invented prestress concrete. Is it difficult to imagine? And this happened in front of you. And you figured out these answers. Now how do you solve the problem? What's the solution? Again, we have to go to France. Who's supposed to be the father of prestress? Eugene Fresnay. But the solution, I think, was found before him. Can you tell me what the solution is? Guess. Now we know the problem. We know the culprits. We know that it's going to fail.
Increase in residual strain carrying capacity.
Now, obviously, we have to increase the residual strain carrying capacity, but how do we do it? What's the, how do you do it? Going slow, no problem. It's interesting, no? What's the use of rushing and finishing the whole syllabus? Go slow. But my people are looking at me because I'm supposed to cover so many slides per lecture, but I'm not able to do it. Tell me, initial classes will be slow. Agreed? But I want you to think on your feet. Give me an answer. Beautiful answer. Mild steel, this is all you can do. Okay, you can stretch that 140 to about 200. That's all. That's not good enough. So there's only one way. If you want to use steel, you have to have a steel which you can pull more. Obviously. What is the ultimate strength of prestressing steel today available? UTS we call it. And yield is pretty close to that, 90% of that. Mild steel, 250. High yield strength deformed bars for reinforced concrete is, well, today 500. Double of 250. Even that's not good enough. Can you guess what's the ultimate tensile strength of the steel used in prestressing? Close to 2000. 1860 is what? 2000. That's really great. 250 became 500, 500 has become 2000. Then you can pull quite a lot and let it shrink by 0.007, who cares? You still are left with, your bank balance is still high, you've not lost it. That's the answer. Adopt a high strength steel with much higher initial strain. This also generates high pre-stressing. But when you pull it a lot and you release it, then there's a problem, that a new problem will emerge. What is the new problem? Huh? Bond you can always have.
We will not get the same strength of bond from.
Wait,
We cannot get same bond strength from the.
you will get it. By the way, we have pre-tensioning and post-tensioning. We'll see that soon. Okay, we'll postpone that question. Bond won't be an issue. You can even have unbonded in post-tensioning. That's a separate issue. But there's another big problem. You solve one problem, another problem shows up. What's the second problem?
We will subject
Huh?
more. Bond will subject more.
No, that creep we can handle because we've seen.
This is the problem again.
How? What's the problem?
Most stresses might be created in concrete.
What do you mean might be? There's no might be. Equilibrium has to be satisfied. You are pulling this a lot, you got a huge. See, the modulus of elasticity doesn't change whether you use mild steel or high strength steel.
Compressive strength of concrete.
Wait. So if the strain is increased multifold, the stress will also be increased. I mean, both ways. You got 2000. Then that force into the cross-sectional area is the tension. That tension has to be equilibrated by pre-compression in the concrete. And normal grade concrete, you'll have to run into trouble, it will crush. So what's the only solution left now? You have to also increase the grade of concrete. So it's historically this is exactly what happened. Earlier they had only low grade. They said they were forced to get into, so if you use high strength steel, you also have to match it with high strength concrete. Adopt high strength concrete. Clear? So we've kind of gone through history in a few minutes and figured out what to do, and you got the answers yourself. Good. Now before we get further into the subject, take a look at something that is available in the lab in your experimental. You have a course on experimental testing, right? All this will be shown to you. But you have two categories. This is called reinforcing steel or rebar. Rebar is a short form nowadays used, of different diameters. And this is the material used for pre-stressing. It looks similar, but it is much higher strength than this. And it can come as a wire. It can come as strands. These three are strands. Strands are wires put together and twined around so that you could get, ideally say 7, or you can get a larger number, right? Or you could get a solid bar. These are the three typical things. But they have high strength and you can pull them and stretch them. Clear? The forms of pre-stressing given in your code. So we have a code for pre-stressing. Did I mention this? IS 1343. By the way, all these codes you should get. And nowadays the soft copy of it is available. The IIT library has got this, and as students you are eligible to download. Am I right? To download and use them. Only thing, when you come to the exam and you take a printout of these, make sure you don't add anything more. Don't add your own code. It will be your own code. No? Don't add to the national building code. That raw code only will be there. No copy. But you're allowed to bring the code. In fact, that's all that you're allowed to do. Okay. So you have wires, pre-stressing wire in a single unit made of steel. Strands, 2, 3 or 7 wires are wound to form a pre-stressing strand. So it's 2, 3 or 7. Tendon, a group of strands. So you can take strands and bring them together. we got a tendon. Tendon is a group of strands of wires are wound to form a prestressing tendon. Right? So now you have much larger diameter, 32 mm. A group of tendons form a prestressing cable. So you can build up on that. You would have seen the giant cable. I'll show you pictures. And bars, tendon can be made up of a single. Tendon is a generic name. You could say cable, you could say tendon. These are common names. You should know these can be commonly used. The diameter of bar is much higher than that of a wire. So this is a 7-wire monostrand tendon. You can see how neatly it is. The cross section is closely packed. 6 on the outside, 1 inside. This one is straight and the others are twined around it. And then there is an anchorage, we'll study that. So there's a multi-strand tendon. Then there's a you can have multi-wire, you can have single bar tendon and so on and so forth. Okay. Next question. Prestressed concrete with embedded steel can be either pre-tensioned or post-tensioned. PSC is what we say for prestressed concrete. What is the difference between pre-tensioning and post-tensioning?
Pre-tensioning also. First tension.
The objective of both is to achieve. We are actually not interested in pulling the steel. Our objective is to put the concrete into a state of pre-compression so that it can counteract the tension that we develop later under load. That's our idea. Is it clear? And there are other forms of pre-stressing other than using steel, such as, they are not so common, but you can use chemical pre-stressing, etc., etc. So if you're using steel, then there are 2 ways of doing it. Pre-tensioning, you have to be careful when you use this word because pretension has another meaning. So it's pre-tensioning, and often they may not use the hyphen between pre and tensioning, but when you speak you should don't say pretension. Pre-tensioning and post-tensioning. Pre means before, post means after. Before what and after what? What's the difference between pre-tensioning and post-tensioning?
Bars are prestressed before casting.
Right.
Post-testing is bars are prestressed after casting.
Okay, very simple. But how can you do that?
Lay a bar and pre-tension and after we pour concrete.
Right?
Whereas in post,
And then what do you do?
we cut the bars.
You cut the bars, or you remove the strains, yeah. And post-tensioning?
Post-testing, we put one duct inside and
Put a duct inside.
and lay concrete over it. Concrete gets started.
Not over it. You leave it in the mass of concrete and you concrete. But you have to make sure this doesn't lose its shape. So you'll have to give some support. Yeah. And then
Concrete gets started. We use tendons in it and we do the duct.
you introduce tendons into the duct and you stretch it in. Very good. You know the answer. Okay, very good. Well answered.